Here we go. So, yeah, welcome to this talk. My name is Stefan. I'm a vulnerability researcher in Sonar's R&D team, the company behind SonarCube. Our vulnerability research team discovered zero-day vulnerabilities in popular open source software that we responsibly disclose to the vendors and use to strengthen our product with new innovation ideas. The focus of our research is on web applications. In general, web applications are potentially prone to a lot of different types of vulnerabilities. These are the common types that we usually encounter. Command injection, cross-site scripting, SQL injection, and so forth. The impact and ease of exploitation of these vulnerability types varies greatly and depends on the environment. But for a few of them, you basically know it's game over once you've discovered them. One of these, which I would generally consider to be a game over vulnerability type, is an arbitrary file write. We still need to figure out what to write where, but usually there are a lot of options. For example, if we are dealing with a PHP application, we can just write a PHP file to the web root. In a Java environment, we might be able to drop a JSP file. Or when dealing with .NET, we could get RC by writing an ASPX file. We could also overwrite a templating file and get RC from that. Or we overwrite a sensitive config file. And even if this does not work, we can leverage more generic techniques and drop an SSH key, add a cron job, or overwrite a user's bash or C file. So there are usually a lot of easy paths to turn a file write vulnerability into code execution. However, today I want to tell you the story of a more challenging file write. Take a look at this small Node.js snippet. The real vulnerability was more complex, but the primitive basically breaks down to this. So what's wrong here? We've got a file write here. The file path is user controllable, and the file content is also user controllable. So in summary, an arbitrary file write vulnerability. I'd already spent some time auditing the application, so this finding was super nice. It should as easily give remote code execution. And I could already feel the rush and excitement of an incoming reverse shell connecting to my machine, and my brain was flooded with thousands of thoughts. Write a JS file, overwrite the config file, add a cron job, overwrite the templating file, drop an SSH key, overwrite an AJS file, overwrite the JSON file. OK, let's just start with the first thought. If we traverse to the source code folder and overwrite the index.js file, so that it executes an arbitrary command, we probably gain, wait, what, 4.3? When using a path traversal sequence, we get a permission denied. It turns out there is a single uploads folder for which the user running the application has write permissions. Everything else except this boring uploads folder is read-only. This makes this very nice arbitrary file write vulnerability pretty much useless. But let's take a deep breath and turn this into a research opportunity. The research question is, could a file write be possibly turned into code execution even though the target's file system is mounted read-only? At first, this may sound stupid, but let's start with a very basic follow-up question. What even is a file? And if you've ever worked with a Unix-based operating system, you're probably familiar with this phrase. Everything is a file. What this means is that a variety of system resources are represented as files. This includes traditional files and directories, but also hardware devices, network connections, processes, and much more. All of these are represented as files. Technically, this everything is a file philosophy is possible due to the virtual file system. The virtual file system is a unified interface for accessing different types of file systems. So if you want to implement your own file system, you would basically need to implement these functions, open, read, and write. These are the basic file operations that are invoked when a user tries to access a file that is part of your file system. How you implement these functions is totally up to you. So there are traditional file systems like Ext4 that stores data on a classical hard disk drive. There are also file systems that support other storage types like UBFS that is used for flash memory. And there are network-based file systems. Although the data is read and written over the network, you can access these files just as usual files that are stored on a locally attached storage. Furthermore, there are special purpose file systems, also known as pseudo file systems, like procfs. Again, procfs only implements what happens when you read or write a file, but in a specific manner that is very interesting for our considerations. So let's give it a closer look. Procfs is usually mounted under /proc and provides an interface to the kernel. It can be used to retrieve real-time information about processes, memory, hardware, and so on. But it also allows us to change system settings by writing to the related file under /proc. And there are some interesting techniques to turn this into code execution. For example, the core pattern file. This file resides under proc this kernel and can be used to configure a name template for core dumps that are created when an application crashes. That is not too useful, but there's an alternate syntax that allows you to configure a program to which the core dump is piped. It's just enough to add a pipe symbol followed by the program to be executed. This can, for example, be used to trigger a shell script. Just write a pipe symbol followed by the script's path to proc this kernel core pattern, and once a segmentation fault occurs, a core dump is generated and the shell script is executed. This is only one possibility, and there are more approaches that are similar. For example, proc this kernel modproc can be used to configure the path to the kernel module loader, which is invoked when a kernel module is loaded. Bin fntmis can be used to gain code execution by configuring a new binary format handler, which again only requires a file write. This has also been used as a container escape. And there is even another to-do file system called sysfs, which is usually mounted under /sys and can also be used in a similar fashion by configuring a helper program that is eventually invoked. So based on this, there seem to be quite a few options to gain code execution by writing to a pseudo file system. But there are some problems with these approaches. At first, writing to all these files requires root privileges. This was already a dead end for our target application because it was running as a low-privileged user. And even if you are root, procfs itself might also be mounted read-only, which is not uncommon at all. This is, for example, by default the case for Docker container where procfs is mounted read-only, and we cannot write to any of the files mentioned here. So in general, these approaches are limited and definitely not feasible in our situation. The cool thing about procfs, though, is that it also gives us access to even more file systems. Specifically, I'm talking about pipefs here. Pipefs is a file system used internally by the kernel to provide, well, pipes. So whenever you enter a shell command with a pipe symbol like this, the shell issues a pipe syscall, which tells the kernel to create a new pipe. The pipe is unidirectional. That means it has two ends, one for writing and one for reading. Because of this, the pipe syscall also returns two file descriptors, one with write permissions and the other one with read permissions. So in this case, the shell binds std out of the cat process to the write file descriptor of the pipe and std in of the grep process to the read file descriptor of the pipe. This way, the data output by cat flows through the pipe to the grep process. Although a command like this is usually executed very fast, the two pipe file descriptors are exposed via procfs under proc pitfd. We can observe this more easily if we run a command like this, sleep 100 pipe cat. If we now listen the open file descriptors for the sleep process under proc pitfd, we can see the pipe file descriptor for writing. If we check the same for the cat process, we can see the pipe file descriptor for reading. We cannot only see these file descriptors here, but we can also read or write to them. So if we, for example, write to fd1 of the sleep process here, which is a pipe file descriptor for writing, our data is read by the cat process, by the pipe, and displayed here. OK, so far we've seen how pipes work and how procfs exposes these. Now it's getting interesting. Remember that our target application is a Node.js application. So let's talk about Node.js and pipes. Node.js is built on the V8 JavaScript engine, which is single-threaded. However, Node.js provides an asynchronous and non-blocking event loop. In order to do so, Node.js uses a library called libuv. This library uses anonymous pipes to signal and handle events. So it also issues a pipe syscall to make the kernel create a pipe. The read file descriptor is then used by an event handler that reads event data from this pipe. Although this is used for internal communication, the related file descriptors are exposed via procfs. So if we spawn a Node.js process, we can see multiple file descriptors here. The file permissions match our low-privileged user which is running the application. So in contrast to the other procfs files, nothing prevents us from writing to these pipes. This even works when procfs is mounted read-only, since we are not directly writing to procfs, but instead to pipefs. The interesting question now is, how is the data processed that we write to these pipes? And here, one specific event handler caught our attention. This handler called UV signal event is registered by libuv to read from one of the pipes. Here's the read call, which takes a pipe file descriptor and a buffer where the data is read from the pipe is stored. This data is assumed to be a sequence of signal messages. A signal message is a simple struct that looks like this. It contains a pointer called handle, which references the signal itself, and an integer called signum. The reference signal data structure is a little bit more complex. It also contains an integer called signum, but what is more eye-catching is this member called signal CB. This is a function pointer. It contains the address of some callback function that is eventually invoked. And if we continue to look at the code, we can see that the signal data structure is retrieved via the handle member, and then there's a check if the signum value of both data structures match. If that's the case, the signal CB callback function is invoked. So let's quickly visualize this. We've got our pipe here. This is the data written to the pipe. This data is split into chunks, which are supposed to be signal message data structures. This structure references a signal data structure, which contains a function pointer called signal CB. Signal CB references the callback functions that is invoked when the signum value of both data structures match. From an exploitation point of view, this sounds very great. We can write any data to the pipe, and there's a quick path to the invocation of a function pointer. And in fact, after we had turned this into code execution, we learned that somebody else had also independently noticed the potential security impact of this. Just recently, HackerOne disclosed this report. Permissions can be bypassed via arbitrary code execution through abusing libuv signal pipes. The scenario described here is a little bit different, but it also uses the same pipe event handler. In this case, the opened file descriptor is leveraged from within a Node.js program to bypass any module and process-based permissions. So basically a sandbox escape. A huge shout out to the author of this awesome report, Xiangyan Li, aka Sign. This guy is doing incredible work. But to be honest, at first, I was a little bit disappointed that the event handler will now be changed and the technique I'm going to show you only works for older Node.js versions. What is very interesting, though, is that even in the scenario described here, which I didn't have in mind, it was not considered a security vulnerability, and the report was closed as informative. That means that everything I'm going to tell you now still applies to the latest version of Node.js and will probably not be changed in the near future. So let's see how we could exploit the event handler with a file write vulnerability. Our exploit strategy looks like this. At first, we write a fake signal data structure to the pipe. Here, we set the signal CB function pointer to an arbitrary address that we would like to invoke. Next, we write a fake signal message data structure to the pipe, and here we set the handle pointer to the signal data structure we've just been written before. For both data structures, we set the signum value so that it's the same and the check before the callback invocation succeeds. At last, we enjoy some nice arbitrary code execution. There's only one problem. We can easily write a fake signal data structure to the pipe and set the signal CB function pointer to an arbitrary address. We can also write a fake signal message data structure to the pipe. The buffer we can write to is actually quite huge. However, we need to set the handle pointer to the address of the signal data structure. And well, we just don't know this address. All data written to the pipe is stored in the stack, and the stack's base address is randomized by ASLR. So without a memory leak, we won't be able to reference our fake data structure. For a one-shot file write exploit, this does not work. What was a little bit surprising to me, though, is that Node.js is by default compiled without position-independent code. The reason for this seems to be performance considerations. There's a closed GitHub issue on this, and the reasoning is that the position-independent code adds a small overhead because of its indirect addressing, which is not acceptable for Node.js. From an exploitation point of view, this means that the address of the Node.js image itself is static. So if we could store a suitable fake signal data structure in this region of the memory, we could correctly populate the handle pointer. But how can we store something in a Node.js segment at a known address? We could search for ways to make Node.js store attacker-controlled data at a static location from an HTTP request, for example, but this seemed to be quite challenging. An easier approach is to just use what's already available. If we examine the Node.js image, we might be able to find suitable candidates for fake signal data structure in the existing data. Our dreams will come true if we could find a data structure like this in the Node.js image. At first, the string that we would like to execute is a command. This would be the first argument to the invoke callback function, since the handle pointer is directly passed to it. This string should be followed by the address of system at the correct offset to overlap with the signal CB function pointer. In that case, we would only need to match the two signal values, and then system would be invoked and the command string as the first, with the common string as the first argument. Of course, the Node.js image does not contain a data structure like this. In fact, it doesn't even use the system function at all, and thus its address is also not present in the global offset table. So we probably need to fall back to a classical ROP chain approach. And the beginning of every ROP chain is the search for useful ROP gadgets. A tool that searches for ROP gadgets usually parses the ELF file on disk and determines the executable sections. The text section is usually the biggest executable section, since it contains the instructions of the program itself. Now the tool iterates over the bytes in this section and looks for a return instruction, for example, since this is a suitable last instruction for a ROP gadget. It then goes back again, byte by byte, from the return instruction to determine all possibly useful gadgets. All these gadgets are output and can be used to build a ROP chain. In our case, however, this is not exactly what we need. What we need is a valid fake signal data structure in the Node.js image, because we have this double indirection. Signal message data structure with a handle pointer to this signal data structure, which in turn contains a callback function pointer. So here at offset hex 60, the signal data structure should contain a valid pointer so that it overlaps with the signal CB function pointer. And this pointer should reference a useful ROP gadget. It is quite a challenging requirement for a data structure like this to exist, but the Node.js binary is also very huge. The recent build here on x64 is a good 110 megabytes. Thus, there is a good chance that we can find a data structure that would be suitable. How can we do this? Well, similar to a classical ROP gadget finder tool, we need to search through the Node.js image. The difference, though, is that we are not only interested in the executable sections like the text section. The memory where the fake data structure resides does not have to be executable. We need a pointer to a gadget. Thus, we can consider all segments that are at least readable. We can also do our search in memory instead of only passing the ELF file on disk. This way, we can also find data structures that were only created during runtime in the BSS section, for example. This may lead to false positives or environment-specific structures, but it increases our chance of getting useful findings, which we can verify manually. A basic implementation of this in-memory search for fake data structures is actually pretty straightforward. Here's a simplified Python script. At first, we iterate over all memory segments, and for each segment, we read 8 bytes at a time, which would be our pointer. On the next iteration, we just proceed 1 byte ahead and read 8 bytes again as our pointer. For this pointer, we check 2 things first. Does it reference map memory? And if so, has this memory the executable permissions? Here, it is essential that the reference memory has the executable permission, because we want to reference a ROP gadget. If both requirements are fulfilled, we read the first bytes from this memory. For these bytes, we determine if they happen to be a useful ROP gadget. If that's the case, we output the address of the fake data structure and the disassembly of the reference ROP gadget. So let me also show you a visualization of this. We read 8 bytes at a time, which we assume to be a pointer. If the reference memory is mapped and has the executable permission, we look at this address and search for a return instruction. If we can find one, we output the address of this fake data structure as well as the disassembly of the related ROP gadget. So like that. Maybe just let's see it one more time. So we read 8 bytes at a time, which we assume to be a pointer, reference the memory, check if it's mapped. If it has executable permission, we check the memory and look if there happens to be a useful ROP gadget, which in this case ends with the return instruction. And like that. Okay, so this is what the script looks like in action. And as we can see, this approach yields quite a few possible fake data structures. The good thing is that we only need one of these that fits our need. What we are looking for is a pivoting gadget. If we can pivot the stack pointer to the data we've written to the pipe, we can continue with the classical ROP chain. So what does this look like? This is the data we write to the pipe, a signal message data structure followed by a classical ROP chain. All of this resides within stack memory. For the signal message data structure, we set the handle pointer to our fake signal data structure, which resides in the Node.js image. This fake data structure contains a pointer to a pivoting gadget exactly at the offset of the signal.cb function pointer. In order to fulfill the signum check before the callback function is invoked, we just need to set the value to match our fake data structure. Once the callback function is invoked, our pivoting gadget is executed, which pivots the stack pointer to the classical ROP chain on the stack. Due to the huge size of the Node.js image, we have access to plenty of classical ROP gadgets and can easily craft a ROP chain. Awesome. So let's gain code execution. I prepared the fake data structure in the ROP chain locally, and everything works fine. So at first, let's start a netcat listener. And now, let's run the proof of concept exploit against the vulnerable target application. So logged in, project created, upload enabled, file written, and boom, nothing. What's going on? I verified everything about the file write, but it seemed fine. Something must be wrong with the payload. So time for some debugging. I attached a debugger to the Node.js and inspected the payload in memory. Damn it. Do you see what's going on here? Have a look at all these 3 byte sequences here. Do you know what these are? UTF-8 encoded Unicode replacement characters. The file write primitive is using the fsWrite file function. This function encodes the output using UTF-8 by default. Since our payload contains a lot of random bytes, these produce invalid UTF-8 sequences, which were replaced with the replacement characters when writing our payload to the pipe via the file write vulnerability. Of course, that messes up our whole exploit. Okay, so basically everything that we write to the pipe needs to be valid UTF-8. For the ROP chain, this is not much of a problem. The Node.js image is huge, and we have access to plenty of gadgets. Just set a bad byte filter and a ROP gadget finder tool, and we are fine. What is not so great, though, is the signal message data structure. The requirements to find suitable candidates that reference a useful ROP gadget were already pretty high, and now we need to further restrict this. Based on this new insight, we need to adjust our script that locates suitable data structures. The base address of the fake data structure needs to be valid UTF-8, so we add this additional check here. Fortunately, there are still suitable data structures, and we can find a nice pivoting gadget. That's how this data structure looks like in memory. The 8 bytes at the beginning overlap with the signal.cb function pointer, and this function pointer references the pivoting gadget. This time, the address of the data structure is valid UTF-8, and we can populate the handle pointer in the signal message. Now we only need to adjust the signal value so that it matches the fake data structure. However, there is another problem here. The last byte of the signal value is hex F0, which is not valid UTF-8. If we try to write this byte via the file write vulnerability, it's replaced with a replacement character, and the signum value check fails. So what can we do about this? if we enter hex F0 in this UTF-8 visualizer, which can be found on our GitHub page, we can see that this byte introduces a 4-byte UTF-8 sequence. Here it says that this is a leading byte for a 4-byte sequence. So UTF-8 parser just expects 3 continuation bytes following this byte. The signal message data structure consists of an 8-byte pointer and a 4-byte integer. Because that's not aligned to 16 bytes, the compiler adds 4 additional padding bytes after the signal integer. These are never processed, and we can set them to whatever we like. So let's just use them and add 3 additional continuation bytes to craft a valid UTF-8 sequence. This floppy disk here, for example, is a valid 4-byte UTF-8 sequence that begins with hex F0 and makes the UTF-8 parser happy. This approach can also be used to make otherwise infeasible ROP gadgets available. For example, this gadget would not be possible on its own because it contains an invalid UTF-8 sequence. However, if we add a pop gadget and a dummy value before it, we can make it valid by introducing a UTF-8 sequence in the last bytes of the dummy value. This way, the stream of bytes will become a valid UTF-8 sequence, and the gadget is fine. Okay. Quite unexpected that a floppy disk plays a crucial role in an exploit in 2024, but now our whole exploit is valid UTF-8 and both signal values match. The callback function is invoked, which is a pivoting gadget to a ROP chain that spawns a reverse shell. So let's see this in action. Hopefully. Maybe not. Here we go. Okay, here's our vulnerable sample application, which is using the fsWrite file function call, which is restricted to UTF-8. The root file system is mounted read-only, and procfs itself is also mounted read-only. Here we are running on node 22.8. but also works for the latest version. And now on the attacker machine, we just use a file-write vulnerability to traverse to proc self fd15, which is a pipe file descriptor for writing, and write our payload there via the HTTP request. So now let's start a netcat listener again, just run our proof of concept exploit, and we gain a reverse shell. Okay, let's come to a final conclusion. The everything is a file philosophy on Unix-based system opens up uncommon attack surface when exploiting a file-write vulnerability. We showcase this with a technique that can be used to turn a file-write vulnerability in a Node.js application into remote code execution. The technique even works if the root file system and procfs are mounted read-only and Node.js is running as a low-privileged user. Since the event handler code is from libuv, this can also be applied to other software that uses libuv. And even without libuv, there are probably a lot of other pipes out there that are just waiting for you to send them some unexpected data via file-write vulnerability. So thank you very much for listening. If you're interested in more of this kind of content, feel free to follow us. We also have a blog where we regularly release new articles on our vulnerability research. Thank you.